My name is Marek, and I'm an engineer at a performance and security company called CloudFlare. CloudFlare provides reverse proxy and DNS services for millions of websites. We have so many customers from so different fields, so from social media outlets through dating portals ending on government agencies. Sorry, this is not right. And being content neutral is very important for us. But being content neutral is not easy. There's always one website being hated by someone. And that's bad. In today's internet, some people try to silence the websites they don't like. And the way to silence websites in today's internet is to launch a denial of service attack. This is a problem because an attack on one of our customers can affect our whole network, all of our clients. This is, of course, unacceptable. We can't just sit idle when our network is under a threat. So we had to do something about it. So we attacked the problem on all fronts. First, we have a very strong trust and safety team. Among other things, they make sure we are not attack vectors ourselves. Then we're always working with internet operators to make sure launching attacks is hard. Then we are always improving our own infrastructure. We add more servers, we improve our performance, and we always add more network capacity. And finally, we do our best to educate the end users. We blog about the new attacks we see, we go to conferences like this one, and try to spread our know-how. This presentation is about a fragment of our wide effort. It's about how we automate our DDoS defenses. So I'll explain how our automatic DDoS mitigation system works and why we build it. So let me give you some context on why automatic mitigations is so important. So the biggest threat to anyone doing anything in the internet is an attack that exceeds the network capacity. In such situation, it really doesn't matter what the attack is composed of. Is it DNS flood or SYN flood or SSDP flood or yet something different? All that matters is that the network will congest and no legitimate packets will be able to flow. And this is extremely bad because such an attack will affect the whole attack network, not only the few attacked IP addresses. Back in the early days, we didn't have a large network. We only had a few data centers. And with limited network capacity, there wasn't much we can do. So when network congested due to an attack, we had a real problem. In order to save our whole network, we often had to sacrifice the attacked IP addresses. So for that, we use BGP now routing. And with BGP now routing, we can pretty much remove the attacked IP address from the internet. This is not perfect, because that means that the services on those IP addresses will be unavailable, but at least the rest of the network is salvaged. But as years passed, we added much more data centers, and we increased our network capacity immensely. And nowadays, we find ourselves in a different situation. Nowadays, most of the attacks actually don't cause congestion anymore. And this is great, because that means we can actually try to do something with the attack. We can actually keep the services under attack available. We don't need to rely on BGP now routing anymore. So let me give you some example. If the attack was an NTP flood, like it was popular a year ago, we could just deploy a firewall rule and just drop the incoming NTP packets. Since the attack don't cause congestion anymore, this will be OK. We don't provide NTP services to our end users. No one will ever notice that there's an attack happening. But there's a catch. Applying more and more specific mitigations requires knowing more parameters. Having to deal with more parameters is pretty hard for the operator. So, for example, to do BGP now routing, all you need to know is an IP address. That's it. But in order to do a firewall rule, now you need to know an IP address, a port number, protocol number, packet length, and maybe even some more sophisticated criteria. And being able to mitigate attacks with better precision is nice, is very good. But having to deal with more parameters is very hard for the operator. So this is where the problem starts. On one hand, the operator would like to apply a very specific and optimal mitigation, but they will need to collect the required parameters. On the other hand, broad mitigations are quickly available. You can always do BGP, now routing, very quickly. But this will cause large damage. Also, it's very easy to make mistakes. In our history, we did have significant outages caused not by the attack traffic itself, but by the operators applying incorrect mitigations. Computers are, of course, much better at dealing with things like that than humans. So many of the DDoS defenses can just be automated. And this is where I step in. For the last 2 years, I've been leading a project to help that. In that time, we've built, from scratch, a fully automatic DDoS mitigation system. It's able to detect attacks as they happen and then mitigate them automatically. The system is called Gatebot, and this is the talk about Gatebot. So Gatebot is composed of 3 components. There is attack detection, then there is reactive automation, and finally there is mitigation. The flow of the action is as follows. On incoming traffic, we are detecting the attacks as they happen. We are identifying them. And this information is being pushed then to the automation system, which is able to pick up a proper mitigation strategy. Finally, this triggers the deployment of the rules across our servers. I'll explain the system in details, but I have to warn you now. So it's easiest to explain, to understand how it works, if I will start with the mitigation phase. So let me start by showing you a real attack and by showing you how we actually mitigate it. OK. So on graphs, big denial of service attacks are pretty easy to spot. They show us gigantic inbound packet spikes, traffic spikes. It's traffic way above the average. On this particular chart, you can see an attack hitting on one of our servers. And in this case, the attack was hitting up to 800,000 packets per second against this single server. So, OK, we see that the attack is pretty large. What was in the packets? It could have been many things. We are seeing different types of attacks. But in this case, it was a DNS flood. In this case, the attack was composed of DNS queries asking my DNS server for a resolution of example.com domain over and over again. So we know how big was the attack. We know what was in the packets. So where are the packets coming from? And this is a big news. So there is no way this kind of volume of packets would ever come from a legitimate application. These packets were actually created by an attack tool, and they're being spoofed and injected into network with a very high speed. In order to keep your application running, it is critical to shield it from the attack traffic. It's just too large. Fortunately, it's usually pretty easy. In our flood example, there are 2 criteria we can use very easily to distinguish the attack traffic from the normal traffic. We can use the attack domain, which is example.com. It's always fixed in this attack. And we can also use the packet length, which is always here fixed at 50 bytes. These parameters can be used to separate the good from the bad traffic. And then, in effect, we can just drop the bad traffic. Since the attack traffic is actually spoofed, it's not legitimate, it's actually a valid thing to do to just drop it. So knowing the parameters, how can we distinguish the good from bad traffic with a very high speed? Well, we could choose one of 2 layers. We could use router and router firewalls for that, or we could choose the Linux and Linux firewall, the iptables. We chose iptables, and we did it for a good reason. So not only it allows us to have very broad criteria, iptables is very configurable, but also we can do deep packet inspection on iptables. This is usually not possible on the router layer. There are many techniques, there are many ways to match packets based on content to do deep packet inspection in iptables. But what we found the most effective is called BPF, the Berkeley packet filter. Here's an example rule, iptables rule that can match based on BPFs. And as you can see, it's just a series of numbers. But these numbers represent a bytecode. And this bytecode is a filtering program. And with BPFs, it's possible to express a fairly complex packet filtering logic. We found BPFs to be extremely effective. And we created a couple of scripts around them. If you are wondering how we actually deal with the DNS attacks, look at our GitHub. It's fully documented there. OK, so now we know that we are using BPFs for mitigations. But that requires updating iptables dynamically. We need to deploy mitigations as the new attacks are created. It's easy to update iptables on a single host, but how to distribute iptables across many machines, across hundreds of machines. For that, we have a different system. We have a centralized mitigation database that allows us to add and remove iptables mitigations from a central place. This is nothing fancy. It's pretty much a glorified interface to our firewall. OK, so now we know how to drop packets in BPFs. Now we know how to deploy the iptables across many servers with our centralized mitigation database. Let's go back to our question, how to detect the parameters automatically. So one thing you could do is you could just log in on an affected machine. If you see something weird going on, you can log into a machine, run TCP dump, and stare at the packets in order to figure out the parameters. But there's a better way. So what we found instead is we are collecting sampled traffic from the switches. And every 1,000th packet crossing our switches is packed on the UDP payload and shipped to our central location. In this location, we can then analyze the packets further and do all kinds of aggregations on that. We are using sflow protocol to deliver the samples to the central location. And then we can use this data to detect attacks automatically. So I'll try to give you an overview of how our attack detection algorithm works. But first, we need to define what is an attack. What do we actually want to find in the traffic? So since we are interested mostly in high-volume packet floods, because they actually cause large damage, we can just use threshold. We can just assume that any attack we want to mitigate is going to be pretty large. Small attacks usually can just be handled by our servers, not requiring any mitigation whatsoever. It's only the big attacks that we want our system to react. Then the system works in such a way that each attack that is detected can be mitigated. There is no need for our system to report attacks that cannot be mitigated. It will be a waste. Additionally, the detected attacks are reported in such a way that could be fed directly into iptables. This is great because that means that the whole system is pretty simple. The most complex logic is in the detection part. But we have to be careful here, because if the detection system detects too many concurrent attacks going on, we may end up in too many mitigation rules, and therefore too many iptable rules. And iptables is not very efficient at handling hundreds of rules at a time. So what should the system do when there are too many attacks going on concurrently? Well, it should aggregate them. For example, there is no reason for our system to report that there are hundreds of IP addresses attacked within one subnet. The system should just say that the whole subnet is being under attack. So implementation-wise, this kind of algorithm is not very simple. There is a well-known algorithm for doing this kind of aggregation called hierarchical heavy hitters, but we decided not to use it. Instead, we devised our own algorithm, which is very simple, but it trades a bit of the accuracy of the reported values for the relaxation of some constraints. So let me give you a flavor of how the algorithm works. The building block for our algorithm is a data structure called space saving. It's an algorithm called space saving. It allows us to keep track of counters for top n entries in an arbitrary data stream. But most importantly, it's only using fixed memory size. We are keeping multiple tables for multiple aggregation levels. So for the sake of explanation, let's assume that we keep 3 aggregation levels. We keep pretty specific IP and port information. We keep less specific, only destination IPs. And finally, the broadest one with attacked subnets. Let's go for /24 subnets. And for the sake of explanation, let's say that our system works like that. So when a new sample comes in, we iterate over all the tables, and we just bump up the counters for each of the table. If the packet was to this IP address, we just bump the counters in each of the tables, and we move on to the next sample. Finally, the system stops every now and then, let's say every second, in order to print out the report. And what it does when it prints out the report? Well, it just iterates over all the tables and finds the entries above some predefined threshold, like, say, 1 million packets per second, and prints them out. So this is how a report could look like. It's not very useful, because you can see duplicated items. Most of them actually overlap. So let's fix the algorithm. So now, instead of bumping counters in each of the table indiscriminately, we are doing that a bit differently. So now when a new sample comes in, we iterate over tables, but in a very well-defined order, from the most specific one to the least specific one. And when we increase the counter in the table we are right now iterating over, then we'd also check the packets per second value. And if it's above the threshold, we stop the algorithm there. If you think about it, this will prevent the counters in the less specific tables to grow. And if you print the report right now, it will actually show some interesting data. So the algorithm is pretty simple, but it's not fully accurate. If you analyze the details, the counters can be off by some fraction, but it works pretty well in practice. Here's a screenshot of some attacks detected against our network, and the point here is that the system works pretty well in practice. It is able to keep the number of detected attacks to a small number, so that the number of mitigations is usually pretty small, but when there are some attacks with very distinct criteria, it is able to figure out them as well. But most importantly, the system scales well. As we are learning more about new attacks, we are able to add more different mitigation criteria, different detection criteria, and the system works very well with added dimensions. OK, let's jump on to the last piece of the puzzle, to the reactive automation. So we described so far two parts of our system. We described the detection part based on sflow, and we did describe the mitigation database that is just pushing rules to iptables. As I mentioned before, the detection system is able to report attacks in such a way that could be just fed directly to the mitigation database. So why don't we do that? Well, apparently you cannot just do that. It's a much more complex problem, because there is plenty of context in each mitigation. Let me give you an example. So for our favorite attack, attacking the example.com, let's assume that the mitigation is just to rate limit those queries. So the naive mitigation could just look at the attack, add a QPS value with some rate limit, and then just move on. Very simple. But if you think about it, where does this QPS value come from? You may want to have different rate limits based on different customers. So for example, if the customer is your very important enterprise customer, you may want to add a different rate limit than if the domain doesn't exist at all, in which case you may want to just drop the packets. So conceptually, you don't have a single input stream for the mitigation rule. You don't have only the attack. You also have some additional data. We can make our system even more complex. So for example, if the domain is actually valid, if we are hosting it, then we may want to whitelist the valid subdomains. But the valid subdomains can change in any moment. The customer can just log into the panel and can change them. So this kind of logic is what we are trying to express in our system. Our system was designed especially to be able to express this logic with extremely simple code. So for that, we created a functional reactive programming engine that is able to execute the rules. The rules are written upfront by either developers or the operators. They are written in a very readable programming language, which is Python. And here's an example of a rule. This rule could be used for our attack that we discussed before. As you can see, it takes 3 input streams. One is the attack, one is the information about domain plans, and finally there is information about subdomains for each domain. And then it does fairly easy string concatenation logic in order to be able to produce the mitigation. When this rule is being run, the functional reactive programming engine will figure out the dependencies, and it will know that if subdomains change for a particular domain, what rules should be recomputed. So perhaps now you can see the power of this system. It's not only easy to read and extend the rules as we grow our systems, but they are also fully composable. So this is a pretty drawing of the setup we are having in our system. There's no way you can read it, but the point is, with small building blocks that are composable, you can actually create a fairly sophisticated system, but you can still maintain code quality. The code is still very readable. OK, let's sum up. So we described all 3 parts of our system. We described the attack detection, we described the reactive automation based on functional reactive programming, and we described the mitigation database. This system is in production for a couple of months. And let me give you some numbers. So here's a chart of daily denial-of-service mitigations as applied by our system. As you can see, some days were pretty busy. It was about 300 times events per day. But the general trend is that it reacts between 1,300 times in our setup. Most of the attacks are pretty small in terms of volume, but we do see attacks that are pretty large. We regularly see attacks hitting us with up to 100 million packets per second. And this kind of attacks is when the mitigation pipeline shines. These large attacks can cause significant damage. And you can only imagine how much time would it take to mitigate these manually. OK, so what are the takeaways? Well, generally speaking, fighting DDoSes is a hard problem. In this talk, I covered only a fraction of a big field, of a big effort we have. And we only covered the technical details of our mitigation pipelines. There's much more work to be done. But I think we are making some progress. And I believe that eventually we'll get there. I believe that eventually we'll be able to fix the DDoS problem in the internet. Thank you.